Clear. I want to talk to you about electric potential. Do you remember when I first introduced the idea of the electric field? And I said part of the way we deal with the concept of the electric field is to talk about force on a charged particle, a test charge, and then remove the test charge and make the idea about the space where the test charge was and not about the charge itself. You remember that whole argument? I want to make a similar argument, but I want to make this argument about something that you already know about that I think might be a good way to bridge what the concept is for electric potential. So I have to dive a little bit into mechanics for this and AP1 for this. So if you've been in either of those classes, you should be fine. If you haven't had a physics class before or you're taking them both right now, there might be some stuff here that I'm going to leave you a little behind on. But I think it'll be okay. I want you to imagine that I have kind of a big hill, all right? We know things about gravity that will make part of this argument pretty easy to understand. If I have a rock and I want to take that rock someplace on the hill, most of you remember from our discussions last year that you have to apply an upward force on the rock that would counter the gravitational force in order to lift the rock and attain some new height above the ground. We would have called this doing work on the rock. You remember? You're applying a force, and if that force causes the rock to change position, then work was done. In fact, the definition of work, and this is worth you guys writing down because something happened last year that I don't want to happen this year, and that was there was mechanics on the E&M test, and students weren't prepared, even though I had said the whole year there's mechanics on the E&M test. There will be mechanics. So the stuff we're talking about right here, if you were in mechanics last year, you'll be fine. If you're in AP1 last year, you'll have to acclimate a little bit, okay? The definition of work is force times displacement times the cosine of the angle. I'm going back to the simplest way to write it. I would have written this as probably in AP1 and even in mechanics, but this assumes that a constant force and a force that is applied at the same angle the whole time is doing the work. In reality, the way I'm supposed to write the definition of work is as an integral to allow for the possibility that the force and the angle at which it's applied may change as the object is moved. Does this jog memories from last year a little bit? I hope so, but I want to remind you that we used this in a manner consistent with two other ideas. The first one was that work can change something's kinetic energy. It was called the work energy theorem. But also, work could change something's potential energy. And let me put a delta in there. The negative sign is important here because in order to change something's potential energy, you have to do work against some kind of conservative force. So if you'll recall this example, this specific one, if you want to lift the rock up and you're causing a displacement in this direction, right, delta x, you do work on the rock by applying an upwards force, and that helps the rock move from where it was to where it is. But gravity is doing negative work on the rock because gravity is pulling downwards while the rock is moving upwards. Follow along? Potential energy is from the reference point of gravity, not you. Meaning the rock gained potential energy because negative work was done against gravity. That's something that had to do with the rock. You lost an equivalent amount of energy because you did the work on the rock to lift it up. But the rock now has that energy. That would have been the argument I made in that class a year ago. Well, 10 months ago. And we would have said that that amount of energy would have been mgh. There are some advantages to talking about energy rather than force, and one of the advantages is that energy is a scalar. When you do this calculation, you are left with a value that is a scalar. Work changes something's energy. Positive amounts of work add energy to the object. Negative amounts of work take that energy away. And it was a pretty straightforward concept. Does that all ring a bell? This all sounds familiar. Now here's something important. Where does the rock have more energy? At location A or location B? If I put the rock at A, will it have the same amount of energy as if I put the rock at B? No. The first question would really probably be, well, it kind of depends. We would talk about that too, right? If you remember, conversations about potential energy were always related to what's the usefulness of that energy. Like right now, you could argue that neither rock has any potential energy. Because if I set the reference level to be where the rocks are, then they have no energy. So one of the things we discussed last year about any conversation related to potential energy was that all conversations of potential energy must begin with a statement of reference. What are we going to call the reference level upon which potential energy is based? Right? We talked about roller coasters. Right? Lifting a roller coaster to a higher location only gives those cars energy if it's possible for those cars to make it back to the lower location, where they could exchange that potential energy for kinetic energy. You guys okay with this argument? All right, so if I say to you, this is our reference level, the ground, then can we all agree it would take more work to lift a rock to B than to lift the rock to A? And therefore, technically, the rock at MGH-A would have more potential energy than the rock at MGH-B. Does that make reasonable sense? So we are comparing it to a reference level common amongst both locations. Everything good so far? Makes perfect sense? Any questions? I think you have a question, so I want to answer it. So, I said it backwards. I'm saying there's more potential energy here than there is here. Is that saying it forwards? Said it backwards. Okay. So, everybody listening to the video tonight, which will be nobody, but I'll just say it. You can write it right down. Today is, September 19th at 1:06. Mr. Sheldon made a mistake. He said something backwards. He's correcting himself right now. It will not be the last mistake. I am confident. I have many more to go. So here's where I want to go with this. And I want to make sure that you have this in your notes. We will need this, all of this. And if you don't remember how these function, I should remind you of how they function. So be honest. Do you need a quick refresher about how these individual things function? Now let's do a quick refresher about how some of these function, okay? So let's start with our definition of work, and let's show where this comes from. And trust me when I say there's good reason to do this, because I'm going to attack this from the standpoint of calculus, and I think it's the right way to go. So you guys from AP1 and from honors physics, this is a good transition, okay? So let's just talk basic for just a minute. I want to talk about a situation in which we are in a uniform gravitational field. Right? That'll help for this. That means that there is a there's a constant force regardless of your height. Does everybody understand what I'm saying? So we're going to lift an object, and to do so, I have to apply a force to the object. I'll remind you here, we only want to give this object enough energy to rise at a constant velocity. We don't need to give it more energy than necessary. So the force I'm going to apply upwards, this is my applied force. All right, that's what I'm applying to the rock, is going to be equal to the downward force of gravity, which we would call weight, and is calculated as the mass of the object times the acceleration of gravity. You guys remember all of those things? Okay. Now, let's, again, assume that I'm going to lift the rock a distance, well, let's just do it from this. Let's do it this way. From H0 to a new position, H1. Everybody okay with this? Now, technically, when I talk about the work being done here, I have to be careful. There's the work I do on the rock. That's this force, right? And there's the work gravity does on the rock. That's this force. I'm interested in the work gravity is doing on the rock. Does everybody understand what I'm interested in? When we're done, the net work on the rock is going to be 0 because the rock's kinetic energy will not have changed, right? We're going to lift it at constant velocity and stop. So our calculation takes place during the realm where the rock is moving at constant velocity. I'm being super specific now. I would not have been this specific in mechanics on purpose, but this class has to be different. All right? So, work is an integral, a summation of the application of a force for each incremental change in displacement. So we move it a centimeter with how much force, and we move it another centimeter with how much force, and we do that incrementally until we've gone from our starting place to our ending place. It's still just a sum. Everybody okay with that? If you want, we can back it up to the way we did this in this class earlier. We can say a small amount of work is done when my force moves the object a small distance. That okay? You understand why I'm writing it this way? I don't see a lot of understanding here, but I want to remind you that I don't have to apply a constant force. I can apply a force that is changing, right? Or I can apply the force at an angle that's changing. All of these things play a role here. Listen, so going back to this will be the amount of work required to lift the rock, a small amount, and I keep adding that up from here all the way to here. That's what this equals. In fact, I'm going to put on my limits, starting from H0, ending at H1. And I'm going to remind myself, this is not multiply. This is the dot product, right? The amount of work done is based on how much of the force is in the direction of motion. So I should write that as all right, small dots now, because it's multiplying. Where the cosine here represents the angle between the applied force, or the gravitational force, and the displacement. We all good so far? Everybody following along so far? Any questions about this? All right. So there's two different works done. There's the work of my force on the object. And we could do that one. We could say the work from the applied force. Is that okay? For that one, I'll put the applied force here. Now that work will depend on how hard I push up on the rock. But if I apply a constant force and I apply upwards the whole time, then those two things stay the same. We good with that? Now this integral super stupid easy, right? There's nothing there, so I assume a 1 is there. And I don't just assume any 1, I assume x to the 0 power. And I can apply the polynomial rule here. I know I'm making lifting a rock the absolute most boring topic ever, because it is. But I'm doing this because you asked, remember? This is the work done by me lifting up the rock. All good so far? Any question yet? Parallel process here. There is work being done by gravity as the rock is lifted. If I add this up, I'm going to have the summation from h naught to h1 of mg cos theta dx. Mg is a constant. The force of gravity pulls downwards the same all the time. So I'm going to have the same kind of integral. Wait, what did I do that for? Sorry. And I have the same thing. We all good so far? All right. Again, a lot of this pure review, but let's make it appropriate for what I need. Got two amounts of work here. Net work, also known as the work done by a net force. Does that sound familiar from last year? So this would be the sum of all the forces acting on an object. Net work would just be adding up the work from different forces. They have the same result, but they're done differently. If you were in my class last year, I would have had like a little chart, remember, with work from one thing and then work from another thing, and I would have drawn a line, said add them together. This is the net work. Jogging your memory a bit? Of course, you could have just found the net force on the object and do the same thing, but this is the one that equals the change in kinetic energy. The work energy theorem requires there be net work done, and that results in the change in kinetic energy. Bringing this up because I'm assuming you remember change in kinetic energy, 1/2 mv final squared minus 1/2 mv initial squared. Good old-fashioned stuff from last year. All still okay. All right, last piece of this puzzle I want you to know. We lifted in the same direction as the rock moved. That'd be the cosine of 0 degrees then, correct? So our work was our applied force times whatever the change in height was. At the same time, the work done by gravity was negative because the angle between gravity and the displacement was 180 degrees. Everybody follow that okay? So, negative mg h1 minus h naught. Now, the net work done was 0 because we said the rock was lifted at constant velocity. But something is now different about the rock. Work was done against a conservative force. So from the rock's perspective, the work done on the rock equals the change in potential energy. This equation only applies to work done by a conservative force. That's the only place that this equation applies. So it doesn't apply to the work I did on the rock. I don't provide a conservative force. I provide a contact force. Contact forces aren't conservative forces. Conservative forces are the fundamental forces of nature. So although I didn't do a a fundamental, so I didn't do conservative work on the rock. Gravity did. So the work done by gravity was negative mg h1 minus h naught. And that has to equal minus the change in potential energy of the rock. This is why last year you'd write potential energy, G equals mgh. But technically, this is the route you had to go to get there. AP1 didn't go this route. Mechanics did, but AP1 didn't go this route. So when we're done, this change, the negative signs cancel out, and we say delta U, the potential energy stored in a rock, is mg h1 minus h naught. We all okay so far? I mean, I just showed you the mgh, right? Not a huge deal. We all know you lift something, it has energy. Why? Because you could let go of it, it could convert that energy right back into kinetic, right? Lift a hammer, let it go, drive a nail, right? You're getting energy back out of the system. The reason I'm bringing this up, and I'm being so diplomatic and careful, gravity works one way, right? It attracts things together. So the force of gravity is never in contest, right? Force of gravity always acts towards the center of the earth. So things that you lift higher have more potential energy because you always know the direction at which they could fall. You understand that's not going to be true with electromagnetic fields, right? Because there's positive charge and negative charge. And because of that, there's going to be positive changes in potential energy and negative changes in potential energy, and it might be based on the fact that our intrinsic property, the thing that causes this force to exist, can be both positive and negative. Mass could only ever be positive. So potential energy might be a little bit more difficult for us to consider. So do you see why I'm being so terribly diplomatic about how we deal with direction and how careful I am? So when you come full-blown confused tomorrow, you can replay this back and say, oh, now I understand. Because I want to get back to something stupid, something obvious, something easy. And I've made a mess of this, so let's make it stupid and obvious and easy. In fact, I'm going to make it this easy. Stairs. Everybody has climbed stairs. Landing. Stair A, stair B, stair C. Okay? There is no energy at A, B, or C. But there's no energy there. But if I lift a ball from the ground and put it there, the ball has energy because it's at A, right? Because work was done to get it there. Is that an okay argument? Does it have more energy if I lift it and put it at B? Assuming we're talking about the same baseline, this is the ground, it's 0, sure. Does it have more energy if it's lifted and put at C? Sure. Look, I'm not trying to confuse you here. MGH. H is higher at C than it is at A. So there's more potential energy for a rock at C than there is at A. What I want you to understand is that there's actually no, oops, I don't want that. There's no actual energy at A, B, or C. The rock has energy because work has to be done on the rock to put it there. But if I show you these stairs and say to you, where would the rock have more energy? You all know that it'd be at C. You guys following what I'm saying? Now, if I put a little rock there, or a big rock there, we know the big rock has more energy than the little rock because the value of M in our computation for energy is different. But we understand each other that there's nothing special necessarily about the space. It's just that it's accessible as being higher than other spaces, right? Here's what I want you to know. We will be talking about electric potential energy in the same manner that we talk about gravitational potential energy. Electric potential energy is going to be based on the work done against an electric field. In the same manner that gravitational potential energy was based on the work done against a gravitational field. The difference is, as you've come to expect, we're more interested in the place than putting objects there. When it comes to electricity, we're often more interested in the field rather than the force. Well, we're going to be interested in something about the space rather than the energy. And we're going to call that the electric potential. Electric potentials are about spaces. Electric potential energy is about objects. My stairs. Do you need me to say that statement again? Electric potential is about space, about a place, a location, while electric potential energy is about objects. Everyone in this room can agree with me that the same rock placed at A, B, or C has different amounts of energy. And that we would all agree that C would be the location where there'd be the most energy if the rock was there, and A would be the location where it'd have the least amount of energy if the rock was there. You can describe A, B, and C as having gravitational potential. We understand C would be a more likely place for the rock to have more energy than A because of its gravitational potential. It's higher at C from the ground than A is from the ground. I don't know how much energy is there. There's no energy there. But a rock, if placed here, would have more energy than a rock if placed there. That's how electric potential works. Electric potential is about a place. It tells you how much energy a charge would have if it were placed there. Let's say that again. It tells you how much energy a charge would have if a charge were placed there. Electric potential is about a place. Here's the hard part. We will define electric potential in terms of electric potential energy. Electric potential is given the capital letter V. That's the symbol for electric potential. Not to be confused with delta V, which is known as electric potential difference. The electric potential is defined as the energy per unit charge. I think you can all probably figure out that UE has to be the electric potential energy, just like UG was the gravitational potential energy. So we will define electric potential as the electric potential energy per unit charge. It's a big topic. Bold strokes today. Potential energy, just like work, is a measure of energy. So we will likely use joules for all forms of energy in here. Flashback to 2 minutes ago. We were doing all this. Just a quick reminder, if we go back to our definition of work, Newton times meter gave us joules. And for you old school people who don't remember, Newton comes from MA, which was kilograms meters per second squared. I know, big duh, just reminding you so you don't forget, because we need all of this. I am assuming you remember these things. If my assumption is wrong, write it down. Because, get all the way over there, back to where I was. Electric potential will be defined as joules per coulomb, also known as the volt. Now, I didn't get to make my big segue, which I'm disappointed about, but I'm going to, while you guys are packing up, because you don't need to write this down, but I happen to have a AA battery for this moment. AA batteries say on the side that they are 1.5 volts. Batteries don't have an electric potential. Batteries provide an electric potential difference, a difference in potential from one end of the battery to the other. This is saying that the change in potential from going from the bottom to the top is 1.5 joules for every coulomb that moves from the bottom to the top, 1.5 volts. Batteries don't tell you energy. They tell you how they will be able to move charge. Okay? All right. That's our introduction.